Welcome to today's class. Today we'll be looking at complex numbers. Complex numbers, we all know, is denoted as C with a cross like this. But today we'll be looking at complex numbers. Well, it's truly complex though. Okay, let's start. The real numbers don't fully serve increasing demand of modern science. The main deficiency is that not all polynomials have a real root. For example, the simple quadratic equation x squared plus 1 equals to 0 has no real roots in the set of real numbers. It has no real roots in the sense that x squared plus 1 equals to 0, x equals to minus 1, x equals to minus 1. We can't find the square root of minus 1. That's why I said the simple quadratic equation has no real roots in a set of real numbers. However, x equals to, when you do something like this, it gives us x equals to plus or minus root minus 1. Formally solves the equation x squared plus 1 equals to 0. Such difficulties can be overcome if the real system is extended by introducing the imaginary unit I, defined as I equals to square root of minus 1, or I equals to square root of minus 1, or I square equals to minus 1. That is, if I equals to square root of minus 1, square both sides, it gives us I equals to minus 1. That's just the logic behind it. Okay, we move on. Complex number is also denoted as C with a slash through it. It's not a big deal though. Representation of complex numbers. There are three basic representations of complex numbers. We have the rectangular form. This is of the form z equals to a plus high b, where a and b are real numbers. A and b are real numbers, where a is the imaginary part, is the real part. A here is the real part, and b here is the imaginary part because it's carrying the I with it. Okay, we go to polar form. Polar form, this is the form z equals to r cos I sin theta, where r is called the modulus of z, where r is modulus of z equals to square root of a square plus b square. You can just formally write r equals to square root of a square plus b square. Then we'll use it in our upcoming example. Theta is the argument of z, where theta equals to argument of z equals to tan inverse of b over a. We use that when we start. Exponential form, this is of the form z equals to r exponential I theta. Z equals to r exponential I theta. Not r exponential raised to power I theta now. Where z equals to r exponential I theta. We're moving fast at this pace. We move to Argand diagram. Argand diagram is like representation of polar form. This in graphical form. Go. Any complex number z equals to a plus high b. I've said it again yet. This is polar form. Basically, polar form. Polar form can be represented by an ordered pair a comma b, and hence plotted on x-y axis, with the real part measured on the x-axis and the imaginary part measured along the y-axis. The graphical representation of complex numbers is called an Argand diagram, named after the Swiss mathematician Jean Argand, who lived from 1768 to 1822. Wow, God be with him. Okay. An example of Argand diagram sketch is what we have here. Z equals to a plus ib. As they've said here, the imaginary part is plotted on the y-axis. This is the y-axis. This is the y-axis. This is the x-axis. write that again. This is the x, okay, x axis, and hence plotted on the x, y axis with the real part measured along the x axis. This is the real part, RE plus RE, and the imaginary part measured on the y axis. This is the positive y axis. Again, now if I have to denote it in graphical form, we have plus, we have minus y minus x plus y plus x. We're not doing that now. We're not doing graph, we're doing complex numbers. And now what we have here is b and we have a here according to z equals to a plus ib. The b is in the imaginary section and the a is in the real section. Tan theta equals to b over a from something like this, twa, choka, twa, opposite over adjacent. Adjacent here is b. No. Opposite over adjacent. Opposite here is what? B. Adjacent here is a. That's opposite b over a. That's your twa. That's your twa. Opposite over adjacent. Well, hoping to use this much more in the example below. First example here says write z equals to 1 plus I in polar and exponential form. Write z equals to 1 plus I in polar and exponential form. Solution. As we all know that polar form is noted as z equals to r open bracket cos theta plus I sine theta. As we all know this, z equals to r cos theta plus I sine theta. Then exponential form. Is also denoted as z equals to z equals to r exponential I theta. So there are three forms. This is already in polar form already. This is your a, this is your b. Your b is 1, your a is 1, your b is 1. Now we are not going to use this much. Now let's move to the solvings. Okay, our question here is z equals to 1 plus I. And when doing questions on complex number regarding solving polar forms, solving rectangular form to polar form or exponential form, the first step you go through is sketching. Please, sketching is the most important thing in drawing, in solving questions on conversion of rectangular form to polar form, exponential form. Okay, now the imaginary part is here, plus I m plus re minus I m minus re, and your a is on the real part, that's 1, and your b, that's 1, is on the imaginary part, that's 1. Then this comes like this. The same thing we have over here, same side. What are we looking for here? Theta for theta. Now let's find our r. As our r is denoted as what? Square root of a square plus b square. That serves us 1 square plus 1. Okay, the best way to do this is just put it in brackets, 1 square plus 1 square, in order not to confuse ourselves. That's 2, that's root 2. We have a 2 over here. Now let's find out theta. Theta has been given us above. Theta equals to tan inverse of b over a, and our b is 1, our a is 1. That serves us tan inverse of 1 over 1. As you all know, tan inverse of 1 is what? Is 45, or pi over 4. That if you take it to radian. Taking it to radian, conversion of theta of degree to radian gives, that's That's theta times pi over 180. If you're converting 45 now, that will give us 45 times pi over 180. That gives us pi over 4. Just try to get this set. Let's note that. Now we've gotten our theta and we've gotten our r. Now let's find our polar form. Polar form gives polar form. The polar form is r cos theta plus I sine theta. From here, this serves us our r to be r equals to root 2 open bracket cos 45. Now let's put it in radian. That's pi over 4 plus I sine pi over 4. We've gotten this ready. We've gotten this set now. Now let's find our exponential form. Exponential form is giving us to be r exponential I theta. That gives us what? R is what? Root 2e exponential I pi over 4. As simple as that. This is the end of the solving. It wasn't hard though. Just finding your z, finding your r and finding your theta, equating them together, making your solution. Let's move to the second example. Write z equals to 1 minus I in polar and exponential form. Write z equals to 1 minus I in polar and exponential form. Okay, solution. Z equals to 1 minus I. First thing I said, we sketch. This is your plus im minus im plus re minus re. Okay, our real part is 1. The real part is 1. Our imaginary part is minus 1. Minus 1. Okay, let me write them up. Real part is 1, imaginary part is minus 1. That comes like this and below. Okay, our angle will be here. Theta. Let's go. Let's find our r. R equals to square root of a square plus b square. Let's go. That's 1 square plus minus 1 square. That's why the bracket is essential and important. This gives us root 2. Let's find our tan, our theta. Theta equals to tan inverse of b over a. That's minus 1 over 1, giving us minus 45 or minus pi over 4. Since we've gotten our theta to be minus pi over 4 and our angle is set to be in the fourth quadrant, fourth quadrant, then and our height is and our theta is in the fourth quadrant. That is, we are going to have. Okay, now let's see this as at time in bearing and distance. We find angles from here to here. That's what we'll be doing here. In this part, you would have found it, but the angle stopped here. Stopped here. That's where we stopped at theta there. Now, since our angle is in the fourth quadrant, if we find the angle of here to here, that's 360 minus theta. Then theta here will be what? 360 minus theta. That gives us 360 minus 45. Okay, a lot of you might think that is minus 45, but let's just forget about the minus and let's just find our angle there. That's 360 minus 45. That gives us 360 minus 45, not 225. minus 45, no, 315, or converting this to radian, we're going to have 7 pi over 4, or 7 pi over 4. So therefore, to polar form, we have our r as root 2 open bracket cos. Our theta is 7 pi over 4 plus I sine 7 pi over 4. This is where we stop at polar form. Now moving to exponential form. We have, what do we have here? We have exponential form formula as r exponential I theta. That will be root 2 exponential I 7 pi over 4. Now you can see this is not really hard. All we just did here was that found our theta and we found the angle coming from here to here. That was just the main part. The angle coming from here to here. And I said we would have found it here, but our angle ended here. When drawing something like this now, and your angle is here, your theta is here, you find the angle from here to here after finding your theta. If you are drawing something like this and your angle is here, and you have your theta, find the angle from here to here. As simple as that. Okay, moving to the third example. Write z equals to -1 plus I in polar and exponential form. Okay, if you feel that the first and second example were enough, you can just pause the video, solve it on your own, then play it and check for the answers. I guess that can be the easiest way to learn or to follow. Solution. Write z equals to -1 plus I in polar and exponential form. Z equals to -1 plus I. First thing we do, sketch. Plus im minus im plus re minus re. This is the positive imaginary side, negative imaginary side, positive real side, negative real side. Okay, I will see that our -1 is on the real side. I know here this is the real part, this is the imaginary part. Okay, I will see that our -1 is on the real part, and this is where it is, -1, and our 1 is on the imaginary part, that's 1. Then let's sketch it out. Let's bring it down. Our angle then goes like this. What are we looking for? Theta here. Now let's find our r. R equals to square root of a square plus b square minus 1 square plus 1 square. Please mind me, when doing this, you don't do square root of minus 1 square plus 1 square. This is wrong. Totally wrong. You put the -1 in the bracket, then r will be square root of 2. Why are we getting square root of 2 these days? Okay, let's go. We found our r. Let's find our theta. Theta I'm going on in the formula from above, tan inverse of b over a. That is tan inverse of 1 over -1, giving us 45, or giving us -45 or minus pi over 4. Now what that's what we're looking for now, angle from here to here. That we should look for. That what theta equals to 180 minus 45. You know we've gotten this angle here as 45 degrees. Let's not forget that we've gotten the angle there at 45 degrees. So theta will be 180 minus 45, giving us 180 minus 45. That will give us 135. Or taking this to radian, that gives us That's 135 times pi over 180. That gives us 3 pi over 4. 3 pi over 4. Simple as that. Now let's find our polar and exponential form. Okay, our polar form is our polar form gives us our polar form formula is saying r and r is what, root 2 open bracket cos theta is 3 pi over 4 plus I sine 3 pi over 4. Now our exponential form states root 2 exponential I 3 pi over 4. Simple as that. Not even up to 1 minute. No, let's say 2 minutes. I'm done with that. What we did, write your equation. Z equals minus 1 plus I. R equals to square root of minus 1 square plus 1 square. R equals to square root of 2. Theta equals to tan inverse of 1 over minus 1. We'll go minus 45. We found the angle from here to here. We find the angle as theta equals to 180 minus 45. That gives us 135 or 3 pi over 4. When taking into it to radian, substituting into this, into r cos theta plus I sin theta, and into this r exponential I theta. It's not that difficult, not too difficult. I doubt if it's difficult. Okay, we go to the fourth or fifth, I don't know. Let's say fourth. Write z equals to minus 1 minus I in polar and exponential form. I'm trying to put all this question into all 4 quadrants. I think I've done the first, second, and third. No, I think this will appear in the 3rd quadrant. Let's check and see. So solution. Let's go. Our formula, our question is z equals to 1 minus z equals to minus 1 minus I. Question can also come in form of z plus 1 plus I equals to 0, and just make z equal to formula by saying z equals to minus 1 minus I. That's all. Don't worry, we'll see questions like this below or in the next example. Okay, first thing we do, sketch. We have our plus im minus plus re minus re plus minus im. We see that they are both negative, and our real part is on the negative axis 1, and our imaginary part is on the negative axis 1, and our real part is on the negative real axis. That's 1. Bringing this out to sketch, and our angle comes like this. Theta comes here. Now let's find out r equals to square root of a square plus b square minus 1 square plus minus 1 square. R equals to square root of 2. We've gotten that, and it's not even more to get us there. So just because our r and our 1, we are using 1, and we know either if it's minus 1 and square root of minus 1 gives us 1. That's why we're getting 2, because of 1 plus 1 gives us 2. Now let's find our theta. Theta equals to tan inverse of b over a, and our b is what? Minus 1, our a is 1. That gives us 45 or pi over 4. Now what do you see we're looking for? Angle from here to here. Let's not forget, people, because it's on the 3rd quadrant. And 3rd quadrant, that will be what? Our theta will give us 270 minus 45, giving us 225. 225, or that's taken into radian. That gives us 5 pi over 4, or 5 pi over 4. Whoa, that's 5 pi over 4. Now taking into polar form, we have polar form. We have our r as root 2 open bracket cos theta is 5 pi over 4 plus I sine 5 pi over 4. And our exponential form we have root 2 exponential I. Theta is what? 5 pi over 4. Not add, just like a puzzle. We found our R and we found our theta. As we all know, mind you, when solving, don't use this theta. This theta you're looking for is from year to year. Okay, theta we're looking for is from there to there because it's on the third quadrant. Okay, moving on. We move to the fifth example. Now we are done on this trick of getting I as 1, the real part as 1, and the imaginary part as 1. I guess this trick has been broken. Okay, we have z equals to 2 minus 2 root 3i. Not add. Let's look at it together. Solution. Question is z equals to 2 minus 2 root 3i. First thing we do, sketch. We have plus im minus im plus re minus re. Minus re plus re. Okay. I will know our real part is on the positive x-axis. That's 2. The imaginary part is negative. That's minus 2 root 3. Sketching this, we have the angle comes here, theta is here. After finding theta, we find the angle from here to here, as we have said above. Okay, let's find out r equals to square root of a square plus b square plus minus 2 root 3 square. Okay, let me use calculator to do this, so this won't take time. That's 2 square plus open bracket minus 2 root 3 square. Okay, that gives us 4. Giving us 4. That gives 4 as our answer, as our R. Now theta, just as formula says, theta equals to tan inverse of b over a, and b is minus 2 root 3 over 2. If 2 cancels 2, we find tan inverse of root 3 or minus root 3. Tan inverse of minus root 3. That gives minus 60 equals to minus 60. Or taking this to radian, we have that's pi over 180. That's pi over 3 when taken to radian. Now this our theta is 60. Now let's find the main angle we are looking for. This theta, that will be theta, because it's in the fourth quadrant, that will be theta equals to 360 minus 60. Whoa, that's a long way. Okay, that gives 360 minus 60, that gives us 300. Or taking 300 to radian, we have 300 times pi over 180. 300 times pi over 180. Taking it to radian, that gives us 5 pi over 3. Now taking this to polar form, we have polar form. Taking it to polar form, we have, and polar form formula states that r open brackets cos theta plus I sine theta close brackets, and our r is what? 4 open brackets cos theta is 5 pi over 4 plus I sine 5 pi over 4. That's our polar form. And our exponential form states that out 4 exponential I 5 pi over 4. As you can see, it's not as hard as you think it is. complex number. This might sound complex, but it's not that complex. Or maybe because we have not reached the complex part, but don't worry, I've got it covered. Moving to the, I don't even know, I've forgotten, I've lost count of the number. Well, we are progressing gradually. Write z minus 1 over 2 minus 1 over 2i equals to 0 in polar and exponential form. Okay, solution. This is looking hard, but let me just mix z subject of formula or subject of the equation. That's z equals to 1 over 2. No, let me write it the way I'm saying it first. Z equals to z minus 1 over 2 minus 1 over 2i equals to 0. Making z subject of the equation, that gives z equals to 1 over 2 plus I over 2, or 1i over 2. So what's the difference? There's no difference though. Okay, let me just clean. I need space because I don't want to leave the question behind when solving. Okay, that's z gives us 1 over 2 plus 1 over 2i. First thing we do, sketch, plus im plus re, because they're both on the positive x-axis and y-axis. Okay, the 1 over 2 is on the positive real axis, that's 1 over 2, and the 1 over 2 is on the second 1 over 2 is on the negative real axis, that's minus 1 over 2. No, it's on the positive real axis, plus 1 over 2 or 1 over 2. Then sketching this, we have dash 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 coming down, angle comes here. Simple as that. Find theta. Now our r will give us what? R equals to square root of a square 0.5 or 1 over 2 or 0.5. Well, let me use 1 over 2. 1 over 2 square plus 1 over 2 square. Therefore, R gives us 1 over 2 square. Let me use calculator. That's 1 over 2 square plus open bracket 1 over 2 square. That gives us root 2 over 2. That gives us root 2 over 2. Well, we can further rationalize and say or 1 over root 2. Yeah, you can get both root 2 or 1 over root 2 over 2, 1 over root 2 in case questions like this come out and they only give us root 2 over 2 and we got 1 over root 2. So just in case, root 2 over 2 also means 1 over root 2 when rationalized. Okay, we found our r. Now let's find our theta. Theta, I said, is tan inverse of p over a. That's 1 over 2 over 1 over 2. Instead of stressing ourselves, this will give us 1. Or let's check. That's 1 over 2 all over 1 over 2 gives us 1. And tan inverse of 1 gives us 45 or pi over 4 when taken to radian. Okay, now let's find our polar form. Polar form, our r is okay, our r is 1 over root 2, 1 over root 2, open bracket, cos pi over 4 plus I sine pi over 4 sin pi. Okay, no, it's sine pi, not sin pi. Okay, too much anime. Okay, that's sine pi over 4. Now let's go to exponential form. I can't spell exponential. exponential form. This will give us our r as 1 over root 2 exponential I pi over 4. It's not that hard. I'll give like 5 seconds to go through it. Z equals to 1 over 2 plus 1 over 2i before I move to the next example. Okay, moving forward, we have the next example as with 3 over 2 plus I1 over 2. Oh, I didn't put z equals 2, but don't worry. From here we have solution. Z equals to root 3 over 2 plus I1 over 2. Why is this one now in the first quadrant? Okay, well, we'll look at that. First quadrant. Now let's go. We have plus IM plus RE. The real part says root 3 over 2 and the imaginary part says 1 over 2 or 0.5. 1 over 2 says 1 over 2. This goes like this, it comes like this. Now we go for this, and we have theta here. Now let's start going further. Find our theta here, find our theta here, find our theta here. Now let's find r. R equals to square root of a square 2 plus b square, that's 1 over 2 square. That gives us open bracket root 3 over 2. Okay, producing this gives us solving this gives us 1. Oh, I'm surprised. After all the whole scary look of the question, the real is giving us 1. Well, let's not fall. Let's find our theta. Theta said it is given tan arctan or tan inverse of b over a. That's 1 over 2 over root 3 over 2. Let's use our laptop, our calculator. We can solve that as tan inverse of 1 over 2 over root 3 over 2. That gives, if solving this, the answer gives us 30. Gives us 30. Oh god, come back. Okay, the answer here gives us it gives us 30 degrees. It gives us 30 degrees or pi over 6. And because the angle came from here to here, I'm not going to, as many as was from the angle came here, would have taken it to here to find here, but the angle stopped here. The angle stopped here, so that's our theta. Then finding polar form. We have our r to be 1 open bracket cos pi over 6 plus I sine pi over 6 sine pi. Okay, let's go. We go to from polar form, we move to exponential form. Exponential form where we have our r as 1 exponential I pi over 6. It's not hard, people. It's not hard, guys. It's not hard, guys. It's not hard. Okay, just logic and step. Do it step by step. It's not hard, just step by step. Okay, I think I made a Gantt diagram clear for solving complex numbers in conversion of rectangular form to polar and exponential form. I think I've made judgment to that aspect. Now let's move to algebraic rules of complex numbers. algebraic rules of complex numbers. Now this first part says let the complex number z1 equals to a plus high b and z2 equals to c plus high d. That's my name. Okay, let's go. Like this, now we are making z and z1 and z2 as the example of these of algebraic rules of complex number. I'm making z1 and z2 the subject of the topic. Now z1 equals to z2 if and only if a equals to c and b equals to d. That is, if for me now, if 2 minus 5i is equal to 2 plus ib or bi, find b. Okay, that is, if 2 minus 5i, oh, this is not plus, this is minus, and this is bi. If 2 minus 5i equals to 2 minus bi, find b. 2 equals to 2 and 5 equals to b, therefore b equals to 5. That is, z1 is equals to z2. I've made judgment to that aspect. Okay, addition and subtraction of complex numbers. Okay, z1 is equals to z1 plus z2 equals to a plus ib plus c plus id. Okay, this will give us, well, they have done it here and I've done the minus here, but let's get proof ourselves and let's see it like, yes, we know we have a plus ib plus c plus id. Since we are adding and we're not multiplying, then resolving the real part and the imaginary part, we have a plus c plus ib plus d. Same thing we have here, correct? Now z1 minus z2 giving us a plus ib minus c plus id. This gives us a plus ib minus c minus id. This then gives us open bracket a minus c plus I open bracket b minus d. Correct. We've gotten this first and the second part. Now let's continue. Multiplication of complex numbers. Multiplication. Before I proceed, I'm sure you guys remember our I equals to root minus 1 and our I square equals to minus 1. I hope you remember that because we're gonna use I square here. Now z1 times z2. Now let's solve it. That's what a plus ib times c plus id kabasa. Okay, let's go. This a times this c here, that gives us ac. This a times this id here, that gives us plus aci. No, that gives us plus aid. Now this ib times this c, that gives us plus cib, and this ib times this here, it gives us plus I square bd. Now let's proceed. We have ac plus, let's say, adi plus cbi plus bd. Our I square is known as minus 1. Then we now have ac plus adi plus cbi minus bd. Now let's resolve them into component of real and imaginary part. Now we have AC minus BD plus I open bracket AD plus CB, or AD plus BC, either BC or CB. Now yes, here we got the same thing they got. Now that's correct. Now complex conjugate. The complex coordinate of z equals to a plus high b is z equals to a minus high b. Or if you have any question and your question states z equals to 1 plus 3i, and they say find the complex conjugate. Complex coordinate, then the answer will be z equals to 1 minus 3i. The sign will just change from positive to a negative sign. I guess we follow that. Now quotient of complex numbers. I guess this is finally the end of the topic of the complex numbers for now. Okay, let's go. Quotient of complex number. Z1 equals to a plus high b. Z over Z2 equals to a plus high b over c plus high d. Okay, it can be simplified by multiplying the numerator and denominator by the conjugate of the denominator. Okay, we solve this the way we solve surge. That's if we all remember. Now let's go. You see Z1 over Z2 equals to a plus ib over c plus id. And they said you multiply both sides by the conjugate of the denominator. That's times c minus id over c minus id. That's the conjugate of the denominator. Then we go again. We say this gives us equals to a plus ib times c minus id all over c plus id c minus id. Solving, we have ac minus aid plus cib minus I square bd. Here we now have c square minus cid plus cid minus I square d square. You have that I square d square. Okay, going forward, what do we have to continue that aspect? Then we know that we have I square here, and I square equals to what? Minus 1. Let's continue. We have ac minus aid plus cib plus bd. The minus 1, if I square equals to minus 1, minus 1 times the minus, that turns to plus. All over, this cancels this minus this, as we are left with c square minus d square. Okay, let's just turn to plus because we have I square. I square gives us minus 1. That minus 1 times minus, that gives us plus. Okay, now we are left with resolving them into different components. We are going to have AC plus BD plus plus BC minus AD all over, no, there's I here, all over C square plus D square. Okay, after revolving this part into both real and imaginary parts, we are going to have AC plus BD all over C square plus D square plus I open bracket BC minus AD over C square plus D square. Solve that. We can look through it. Any problem? I guess there isn't any problem because you can't answer through here, but you can answer through the comment section If you're having any problem with any part, reply, just write on the comment section the part you have problem in. Now we see in the next part when we are moving into the movers theorem. Okay, I hope this class was good enough for us. We're moving to the movers theorem. In next class. Arigato. Thanks for today's class, and I hope we all achieve one or two things. I hope you haven't living here the same way we came here. I hope you gained more. Thank you for watching, and please like, comment if you have any problem on the video. Please comment if you have any problem on the video, and please subscribe and share to your friends who you think don't understand or who you think want to learn more. Thank you, and please subscribe to see more from my channel. Okay, that's all for today. On our next class, we're going to move to the movers theorem. Complex number, we're going to move to the movers theorem.